Dear students, in this lecture, let us understand the simplex method of providing solution to linear programming problems, commonly called LPP. It is important to know that the simplex method is simply an extension of the graphical method taught in the previous class. Historically speaking, it may interest you to note that the existence of optimization methods, of which LPP is a part of, can be traced to the days of Newton, Lagrange and Cauchy. Although various methods existed, the advent of high speed computers in the 20th century made the implementation of complex optimization and LPP procedures possible. This further led to greater research on the subject and the development of newer methods. Let us discuss one such well defined method in linear programming problem, the simplex method, today. Typically, the simplex method is applicable to any dimensional engineering problem in different disciplines, while graphical method is applicable to two-dimensional LPP only. As we had discussed earlier, it is important to recollect the fundamental components of an LPP. These fundamental components are integral to a simplex solution procedure. Let us take these three fundamental components one at a time. Firstly, an objective function expresses the main aim of the given problem, which is to minimize or maximize. For example, in a civil engineering example, they represent the minimization of cost or maximization of the profit. Let me elaborate further. In designing a bridge pier, the objective function will be to maximize the strength or to minimize the size. Secondly, a set of unknowns or variables controls the value of the objective function. In the example of a bridge pier, the variables are shape and dimensions of the pier. Lastly, a set of constraints allows the unknown to take on certain values but exclude others. In a typical bridge pier problem, one would want to limit the breadth of the base and to constrain its size. The optimization problem is then to find the value of the variables that minimize or maximize the objective functions while satisfying the constraints. It is interesting to observe that the objective function is a mathematical function. One wants to maximize or minimize subject to certain constraints. Many optimization problems have a single objective function, but there are two exceptions that we need to know. Firstly, no objective function. In some cases, such as design of an integrated circuit layouts, the goal is to find a set of variables that satisfies the constraints of the model. The user does not particularly want to optimize anything, and so there is no reason to define an objective function. This type of problem is usually called a feasibility problem. Second, multiple objective functions. In some cases, the user may like to optimize a number of different objectives concurrently. For example, in the optimal design of a panel of a door or a window, it would be good to minimize weight and maximize strength simultaneously. Usually, the different objectives are not compatible. The variables that optimize one objective function may be far from optimal for the others. In practice, problems with multiple objectives are reformulated as a single objective problem by either forming a weighted combination of different objectives or by treating some of the objectives as constraints. Let us now focus on linear programming, which is the most useful optimization technique used for solution of engineering problems. The term linear implies that the objective function and the constraints are linear functions of non-negative decision variables. Thus, the conditions of linear programming problem are: firstly, objective function must be linear function of decision variables. Secondly, Constraints should be linear function of decision variables. And finally, all the decision variables must be non-negative. For example, maximize z equal to 6x plus 5y subject to constraints 2x minus 3y less than or equal to 5, x plus 3y less than or equal to 11, 4x plus y less than or equal to 15, and the non-negativity constraint x comma y greater than or equal to 0 is a typical example of a linear programming problem. However, the standard form of the LPP must have the following three characteristics. Firstly, objective function must be a maximization type. Therefore, if there is a minimization problem, it should be converted into a maximization problem by multiplication of the entire function by minus 1. Secondly, all the constraints should be of equality type. Introduce slack or surplus variables to reduce non-equality equations to equalities. Thirdly, all the decision variables must be non-negative. If any decision variable is negative, then introduce two non-negative variables such that the decision variable becomes non-negative. Let us now understand the canonical form of the linear programming problem. In simple English, the term canonical means according to rules or acceptable procedure. To understand simplex method, an understanding of the canonical form is important. In the canonical form, the given set of equations can be transformed in such a way that a new set of different equations are obtained, each having only one variable with non-zero coefficient. This is achieved by some elementary operation. With this background, we are now prepared for learning the simplex method. It is perhaps the most popular method used for the solution of linear programming problem. It is worthwhile to recall a lesson from one of the earlier classes that the optimal solution of an LPP, if it exists, lies at one of the vertices of the basic feasible solution. As inspection of all solution one by one is not practically feasible, simplex method offers a solution procedure using the simplex algorithm. In simplex method, starting from one basic feasible solution, one follows the shortest route to reach the optimal solution. Please note that the shortest route consists of a sequence of basic feasible solutions generated by simplex algorithm. The general procedure of simplex method is explained in 4 steps. Step 1, convert the general form of the given LPP into its canonical form. Step 2, find a basic feasible solution from the canonical form. Step 3, move the initial solution to an adjacent basic feasible solution which is closest to the optimal solution among all other adjacent basic feasible solution. Step 4, repeat the procedure till the optimal solution is arrived at. Let us solve a linear programming problem by using simplex algorithm. The given problem is maximize z equal to 4x1 minus x2 plus 2x3 subject to constraints 2x1 plus x2 plus 2x3 less than or equal to 6, x1 minus 4x2 plus 2x3 less than or equal to 0, 5x1 minus 2x2 minus 2x3 less than or equal to 4, and the non-negativity constraint x1, x2, x3 greater than or equal to 0. Firstly, let us transform the LPP into its standard form. The equations now become z is equal to 4x1 minus x2 plus 2x3, 2x1 plus x2 plus 2x3 plus x4 is equal to 6. Thirdly, x1 minus 4x2 plus 2x3 plus x5 equal to 0. 5x1 minus 2x2 minus 2x3 plus x6 equal to 4. And lastly, x1, x2, x3, x4, x5, x6 greater than or equal to 0 as per non-negativity constraints, where x4, x5, x6 are slack variables for converting inequalities to equalities, which we discussed earlier. Now we will convert the set of equations into the canonical form. The equations after conversion now becomes 4x1 minus x2 plus 2x3 plus 0x4 plus 0x5 plus 0x6 plus z, the objective function, is equal to 0. The second equation will appear like 2x1 plus x2 plus 2x3 plus 1x4 plus 0x5 plus 0x6 is equal to 6. The third equation will appear like x1 minus 4x2 plus 2x3 plus 0x4 plus 1x5 plus 0x6 is equal to 0. The last equation will look like 5x1 minus 2x2 minus 2x3 plus 0x4 plus 0x5 plus 1x6 equal to 4. The algorithm now examines three important points for each iteration. The first point is there a possibility of further improvement to the optimal solution? As an answer, we need to check the objective function. If any of the objective function coefficients is negative, then the optimal solution can be further improved. The second point is to decide as to which of the non-basic variable is to be entered into the system called the basis. As an answer, the variable having the minimum coefficient is to be entered. The third point is to decide as to which of the basic variable is to exit from the system. As an answer, the variable having the minimum BR by CRS ratio is to exit. Using the explained procedure, the given equations now become 0x1 minus 15x2 plus 6x3 plus 0x4 plus 4x5 plus 0x6 plus objective function z equal to 0. The equation 2 becomes 0x1 plus 9x2 minus 2x3 plus 1x4 minus 2x5 plus 0x6 is equal to 6. The third equation will become 1x1 minus 4x2 plus 2x3 plus 0x4 plus 1x5 plus 0x6 equal to 0, and the last equation will appear as 0x1 plus 18x2 minus 12x3 plus 0x4 minus 5x5 plus 1x6 equal to 4. Thus, a basic feasible solution is obtained to the given problem. After the completion of this iteration, it is noticed that the objective function still has minus 15 as one of the cost coefficients in the objective function. Therefore, it can be concluded that the optimal solution can further be improved upon. After repeated iterations, the solution reaches its final optimal solution. For the given problem, the final equations will come out to 0x1 plus 0x2 plus 0x3 plus 1x4 plus 1/3 x5 plus 1/3 x6 plus objective function z equal to 22 bar 3. Second equation 0x1 plus 0x2 plus 1x3 plus 1/4 x4 plus 1/8 x5 minus 1/8 x6 is equal to 1. The third equation will appear like 1x1 plus 0x2 plus 0x3 plus 1/6 x4 minus 1 by 36 x5 plus 5 by 36 x6 equal to 14 by 9. The last equation will appear like 0x1 plus 1x2 plus 0x3 plus 1 by 6 x4 minus 7 by 36 x5 minus 1 by 36x6 equal to 8 by 9. It is now seen that all the coefficients of the objective function are positive, hence the optimal solution to the given problem is obtained. The optimal solution for the given LPP problem is z equal to 22 by 3 with the values of x1 as 14 by 9, x2 as 8 by 9 and x3 as 1. To conclude, we have seen as to how the simplex method can be used for linear programming problem. There are different types of practical engineering situations which can be converted into linear programming problem and solved by the simplex method. Please practice this in your own time. Thank you.